just like we have the concept of powers of numbers, we also have the concept of powers of matrices. So the concept of powers of matrices is basically a matrix multiplied by itself a total of n times. And believe it or not, matrices also have interpretations where the power is not just numerical but also decimal. But we're not really going to get into that interpretation here. However, as you can imagine, the amount of computation that is involved in this is insanity. Imagine I asked you, find a to the 100. Are you really going to compute the matrix multiplication 100 times? I mean, that's a lot of computations. Suppose I have a 10 by 10 matrix, right? We know that we have to make we have to compute 100 elements just to do the multiplication of two of the matrices. So one multiplication costs us a minimum of 100 inner product computations, and one inner product computation for that example would consist of 10 multiplications in and of itself. So you're talking about 1,000 computations just to find the 10 by 10 for one multiplication. Imagine doing that 100 times. You're talking about 100 times 1,000, and you have 100,000 operations. That's too much, right? Too much. So as it turns out, if we want to take the power of a matrix, first of all, we can realize that the matrix can be decomposed, right, into our eigenvalue decomposition. And so we know that we're doing this a times a times a, n times. Well, if we were to rewrite each a in terms of its eigenvalue decomposition, okay, and we do that n times, notice that for each time, the C inverse C multiplies to I, which just goes by itself. It goes away because it goes to identity, and anything times identity is just itself. So what we end up getting is this here, which is the diagonal matrix that's multiplied by itself n times. However, what's interesting about any diagonal matrix, regardless of how many there is, and I'll illustrate this with just a 2 by 2 matrix so you can kind of see it, okay? So notice that if I multiply this diagonal by itself, what do I get? Well, let's see. A times A is A squared, plus 0 times 0, so we just get A squared. A times 0, B times 0, so I get 0. A times 0, B times 0, I get 0. 0 times 0 plus B times B, which is B squared. And if I multiply that again times A0, AB, you'll notice that I get A cubed, right? A cubed plus 0, 0, 0, B cubed. And so what's the point? The point is that the power of a diagonal matrix, if A is or to keep it separate, if B is a diagonal matrix, where I have A1, A2, or AN, okay, whatever it is, then when I take B to the M power, that's just this very easily taking the diagonal elements to the M power. So that's very easy and nice to compute. So what I get to compute the power of a matrix is very simple. It's just taking the diagonal matrix and multiplying the left and right by the eigenvalues / vectors. So how do I compute the matrix 1, 2, 4, 3, the one we had before, taken to the 100th power? We first find the eigenvector, which I honestly don't remember what that was off the top of my head. I think it was this, and I definitely do not really remember the inverse, but whatever that was. And then you have the 5 and the -1 here. And if you wanted to do that, you take 5 to the 100 minus 1 to the 100, and then multiply out the rest, and you get your answer very, very quickly. So, moral of the story, if you want to take powers of matrices, one of the ways that you can more easily do this is by first converting the matrix into its eigenvalue decomposition form, and then just simply taking the power of the eigenvalues, or taking the eigenvalues to the same power. Then multiply that out by the matrix of eigenvectors and the inverse of the matrix of the eigenvectors.